Hello. Let's go ahead and continue with a new section 6.1, solving systems of two linear equations using substitution or elimination. Our objectives are 1, solving linear systems of two equations with two variables by graphing. 2, solving linear equations with two variables by substitution. And 3, solving linear systems of two equations with two variables by elimination. Linear systems and graphing. The first 5 sections in this chapter will be mostly entirely devoted to one type of problem, solving linear systems of equations. To solve a system of equations means to find the solution or solutions that satisfy every equation in the system. We will start this section by graphing to solve systems of two linear equations and two variables. So let's start with this first example. Use graphing to solve linear systems. So I have y equals 3x minus 1 as my first equation, and we have 2x plus y equals 4 as our second. For our second, let's go ahead and change it so that it's in that y equals mx plus b form, so that's easier to add. So you would have to subtract 2x, subtract 2x. You would have y equals minus 2x. You have a positive 4, so plus 4. Just as we have below. So I have my first and my second. Let's graph them. So for the first one, I go to my y-intercept of negative 1. I have a slope of 3, so I go up 3 over 1. 1, 2, 3, and then to the right 1. For the next, I have a y-intercept of positive 4. And I have a slope of negative 2, so I go down 2, 1, 2, and to the right 1. We see that these particular points lines meet at a special point. And we can see this point would be negative 1, comma, it's up 2 units, so negative 1, comma 2. Where they meet, that would be our answer. So we're looking for the point where they cross. However, this comes with problems. Though graphing is one way of solving equations, it's not always the best. Because while this one was relatively easy to follow, because the lines meet at a specific point, but what if that point were a fraction? Or what if you don't have access to graph paper? Then it would be a bit harder to find. Such as our next example. We have our two lines, and if we graph them and write them in slope-intercept form, we get these two equations. And if we graph them, let's see where they meet. Oof, that's hard to tell. I can tell. I know it's some type of fraction. So how do we find the answer? To answer the system is a single point where these two lines cross. By inspection, it's very difficult to determine the ordered pair solution. The actual answer is negative 1/2 and 2 over 9. But graphing is not a method that allows this accurate determination. So why did we start this chapter considering graphing as the first method for solving linear systems? Based on the following discussion about graphs of two lines, every system of linear equation will have 3 different outcomes. So let's look at this example. So one of our outcomes can be, well, what if they have the same slope? Remember, if they have the same slope, they'll be parallel lines and they won't cross. So if we have two parallel lines will never cross, there's no such point where they'll meet. So this would be an example of no solution. Or we can have two different lines and have them meet at a special point. If so, two lines will only be able to meet at one point. So we have one solution. Our other option is if we have two graphs and strangely enough, our two equations, do they look similar? They're exactly the same. If they're exactly the same, then the two graphs would overlap. And so every single point that you can imagine that exists on these lines would be an answer. So for that, we say there are infinitely many solutions. When you see infinitely many solutions, it means they're the same line. In general, the following describes three possibilities for solutions for every linear system of two equations and two unknowns, as well as introduces a mathematical terminology used for each situation. A. Two parallel lines have the same slope and different y-intercepts. So if they have the same slope, we say that there's no solution and it's inconsistent. They can also have different slope, and if so, there is an answer in an ordered pair. Also, our last option is it can be the exact same graph. The exact same graph. And if so, there'll be infinitely many solutions, and it's called dependent. All right, so now we're going to focus on learning how to find the answer without graphing. Our first method is substitution. Graphing showed three possible outcomes for linear systems, but lacked accuracy in determining the solutions. We will now consider substitution, a method that will allow us to determine the exact answer to every linear system. So for substitution, we can describe the process of substitution as follows. First, we want to pick an equation and solve for one variable. So that means get x or y by itself. Isolate it. 2. Substitute the expression for the isolated variable in step 1 into the other equation. So you have one that's equal to one letter. Plug it into the other equation. 3. Solve it. 4. Substitute back into the equation of the second variable. So let's take a look at example 3. Solve the system by substitution. So as I look into my two equations, looking at my x's and my y's, is there one that would be easier to get by itself? Maybe a variable that doesn't have a coefficient? And there is, right? We see that we can get x by itself by simply moving that 4y, by adding 4y to both sides. And so we get x is equal to 4y plus 13. So something that it doesn't really emphasize, something that I feel it's truly helpful is label your equations, equation 1, equation 2. So our equation 1 is now this. So we're going to take our equation 1 and plug it into the other one, equation 2. So we're saying that x is equal to all that. So we're going to take that value of x and plug it into the x of my second equation. So for x, I'm going to plug in 4y plus 13, as we see here. And make sure you use parentheses. It'll keep you from doing a silly mistake. Now you're left to distribute. 3 times 4 gives you 12y, and 3 times 13 gives you 39. So now we're here. Now we have to clean up our work. 12y plus 39 plus 2 equals negative 3. Our next step is to solve. So notice that you're in terms of y, so solve for your variable. In this case, it's a y. So we can add our 12 and our 2, we get 14. Now we have to move our 39 to the other side, minus 39, minus 39, and we get 42, negative 42. You divide by 14, divide by 14, and we get y is negative 3. All right, we're going to take that and plug it into our other equation. So it doesn't matter which of the other forms it is. It can be our original given one, but it would be easier if we use the one that we solved for, because that would produce an answer right away without having to do much algebra. All right, so we have that y equals negative 3 from our answer, and our other equation is x equals negative 4y plus 13. Let's go ahead and plug a negative 3 in for y. We clean up our work and we get x equals 1. So our two answers are x equals 1 and y equals negative 3. Remember, our answers are always given as a point, so x comma y. So the answer is 1 and negative 3. All right, let's do example 4. Solve the following linear system by substitution. All right, so I want to pick a variable that'd be easier to work with, and for this one, there isn't a variable that's by itself. So whether you choose to solve for equation 1 or equation 2, it seems that they'll be equally as challenging. All right, let's choose the second equation and solve for y. If we solve for y and we get y by itself, we have to move the 7 and then divide by a negative 2. We get y equals 7 over 2x plus 3. That's our first equation. All right, let's plug that into our other equation for y. So instead of y, I'm going to write my equation as we see here. Now I have to do some algebra to clean it up. So I distribute the 3, and we're left with 5x minus 21 over 2x minus 9 equals 2. Since the equation contains fractions, it may be simpler to solve by multiplying and distributing a 2 on both sides. So what it's saying is, since we have that 2 as a denominator, multiply both sides of your equation by your greatest common denominator. So multiply both sides by 2 and distribute that 2. So 2 times 5 is 10x. That 2 cancels out. We have 21x. 2 times 9 minus 18 equals 4. All right, now you can go ahead and work without having to deal with that fraction. So 10 minus 21 is negative 11. Minus 18 equals 4. Let's add 18 to both sides. And we're left with negative 11 equals 22, so x equals negative 2. So let's take back and plug in negative 2 into our start equation, which we labeled with a star. And so we're going to let negative 2 be replace the x. So we're left with y equals negative 4 as an answer. And remember, you always want to write it as x comma y. So this is our answer. Our next method to solve linear equations is elimination. Well, technically it's a third because the first one was graphing. Forgot about that one. And the second one was substitution. All right, so that leaves the third one to be elimination. The third method we will discuss in this section is elimination. To introduce the process of elimination, we will consider the following system of equations. So we have x plus y equals 5 and x minus y equals 1. If we consider the second equation as saying x minus y is the same as 1, algebra allows you to add x minus y on the left of the first equation as long as we add up to 1 on the right side. For simplicity, this idea allows us to line up the equal signs and add up the two equations below. So we have equation 1 and equation 2, and let's add them vertically. So we can go ahead and add our x's, add our y's, and add our constants. We see that x plus x is 2x, and in the middle we have y minus y, that adds up to be 0, and lastly we have 5 plus 1 is 6. Because coefficients of y in the two equations are opposites, this addition eliminated y. We now have the equation 2x equals 6, where we can divide both sides by 2 to determine that x equals 3. Using back substitution for x equals 3, the equation x plus y equals 5, we replace the x with the 3 like we said, and we get y equals 2. So we have now done substitution. So the goal is to make one of them cancel out, just as we see here. My y's canceled out. What you're left with produced a different equation. So we have 2x equals 6, since that's what we have left over. We get that x equals 3, and then take that number and plug it into your equation to find your remaining piece. The most important takeaway from this example is the addition of two equations resulting in elimination of a variable because of the coefficients of this variable, and two equations are opposites, meaning like 6 minus 6 gives us 0, such as negative 6 plus 6 gives us 0. We see that these numbers, they're opposites, right? Negative 6, they're the same number, but one is positive and one is negative. So you want to add two numbers that are the same but different sign. All right, so what are our steps? Let's read the highlighted portion. So 1, I want to multiply one or both sides by a constant so that one variable will have coefficients that are opposites. 2, add two equations. 3, solve the resulting equation. And 4, back substitute to find the value of the second variable. Example 3 again. So let's solve this linear equation. So if I look at my numbers and my x's, and I look at my y's, they don't add up to be 0. So I have to multiply something to one or both of my equations so that I can make a 0. Well, if we multiply a second equation by 2, which we say here, if I multiply my second equation by 2, what happens? Well, 3 times 2 gives us 6, and 2 times 2 gives us 4, and 2 times negative 3 gives us negative 6. And notice what happened with our y's. My y's are now a positive and a negative copy of the same number. So if we add our equations, x plus 6, if we add them vertically, x plus 6 gives us 7x. 4y minus 4y, that's 0, so that's gone, is equal to 13 minus 6. That gives us 9? 7? 7. 7. So we're left with 7x equals 7, which we have here. And if we divide by 7, we get that x equals 1. Back substitution of x equals 1 into the equation. So we can go ahead and plug into our equation. Which one? It doesn't matter. Just pick one. It works out every time. We plug it back into our equation, and we get that if x equals 1 and we plug it into one of them, let's plug it into that second one. We get that y is equal to negative 3. Remember to always write your answer as a coordinate point. All right, let's do example 4. Solve the following system by elimination. Again, we see if we look at our numbers, they don't add up to be 0 automatically. So I have to multiply something to one or both of them. 2 and 3 make me think of 6. So let's go ahead and try to create a 6. If I multiply the first one by a 2, such as we see here, we'll get a negative 6. If we multiply a second equation by a negative 3, that'll give me a positive 6. So I have forced a positive and a negative for my y's. And it seems like we did y's both times. You could choose to be x or y, whichever one catches your eye. All right, so if we add them, we get that 10 minus 21 is negative 11x. My sixes are gone, and we're left with 4 plus 18 is 22. So we're left with negative 11x is equal to 22. We get x is negative 2. All right, let's plug in -2 into either one of our equations. Let's choose this one. We plug in a 2 for x, -2 for x. We get -5 times -2 minus 3 equals 2. We get -10 minus 3y equals 2. We add 10 to both sides. We get 3y. -3y equals -2. We divide by -3. We get y is -4. So this is our answer. All right, let's talk about some special cases. Inconsistent and dependent systems. At the start of this section, graphing was investigated as a method to solve linear systems of two equations in two variables. Although the method lacked accuracy, the graphs of two lines showed that three possibilities for the number of solutions to a linear system are none, one, or infinitely many. However, every example in this section has resulted in a single solution. We will now discuss linear systems that have no solution or infinitely many solutions. Systems are called inconsistent and dependent, respectively. All right, so let's go ahead and work on example 5. Let's try to solve using elimination. All right, so let's multiply the first one by -2 because I want to make those 0. All right, so I'm left with -6x minus 10 equals +4, and 6x plus 10 equals 3. My 10s are gone, and we're left with -6 plus 6. Oh, it so happens that my 6's are gone too. So we're left with 0. And on the other side, I'm left with 7. So we're left with a statement. Is 0 equal to 7? No. 0 is never equal to 7. And if you're ever unsure, think of money. Is $0 the same as $7? Not at all. Right? So we have a contradiction. This is a false statement. Allows us to determine that the given statement has no solution and is called an inconsistent system. So in other words, no solution. And if you're asked if it's an inconsistent or consistent system, it's inconsistent. Example 6. Solve the following system. All right, we see that y is by itself, so let's go ahead and use substitution. Let's take this set of numbers and plug it in for our y. All right, if we do so, we're left with this here. All right, let's distribute our 3. And we see that my 3's cancel, and we're left with 2x minus 2x minus 3 equals 3. We combine our like terms, 2x minus 2x, well, those add to be 0. And we're left with -3 equals -3. Is -3 the same as -3? Yeah, they're the exact same number, they're equal. We have an identity. This is a true statement and allows us to determine that the given system is infinitely many solutions. And it's called a dependent system. We could describe the set as follows. You don't need to do this part. Just know that you have infinitely many solutions, and it's a dependent system. All right, because we're kind of short on time, I'm skipping applications, so stop here. Check your homework assignment so you know what problems to do. It's not going to involve the word problems for applications. All right, that's it for this section. Remember, we learned about graphing, solving using graphing, substitution, and elimination. However, graphing isn't the best one. So as you're doing your homework, make sure you're practicing either the elimination method or the substitution method. Those are the ones that you need to practice and become familiar with. Thank you.